In this video, in this clip, we're going to discuss the similarities and differences between nucleophiles and bases. Well, essentially the definition of a nucleophile is the opposite of an electrophile. A nucleophile, in general terms, is an atom or a group of atoms that is electron rich, and it seeks positive centers. Hence the name nucleophile, because nucleuses are positive. Generally, nucleophiles attack an electrophile, so one of the requirements for something to be a nucleophile is that it must possess a lone pair or a pi bond. So a nucleophile generally attacks, and generally nucleophiles are negative, but they could be neutral also. A nucleophile attacks an electrophile with its lone pairs and makes a nucleophile electrophile bond, and this is essentially a lot of the reactions that we learn in organic chemistry. It's basically a nucleophile attacking an electrophile. Generally, in the reaction when we're considering substitution versus elimination, and we said the substitution requires a nucleophile and elimination requires a base, a nucleophile attacks a carbon. To review what a base is, the definition of a base, and here we're talking about entities that abstract protons. The definition of a base is that it abstracts or removes or accepts a proton. Now, these are the definitions, but essentially, as we have previously learned, a base or a nucleophile, which is represented by the symbol nucleophile, a nucleophile is essentially the same as a base. Or in general, nucleophilicity, which is the ability to attack an electrophile, nucleophilicity is generally and essentially parallel to basicity. Things that are strong bases, molecules or groups of atoms that are strong bases, are generally also good nucleophiles, because these properties go hand in hand. Good and strong bases are generally negative. They have a strong affinity for a hydrogen atom, and generally the same will be true that if something is a good base. An example is an OH. This group of atoms or this molecule has a high affinity for a proton. It's a strong base, and the same properties make it a strong nucleophile or good nucleophile. It's also good at attacking an electrophile. And if you remember the trend, generally speaking, in the periodic table, basicity is the opposite of acidity. So acid strength increases going across the table and going from top to bottom. If that's acid strength, base strength is generally the opposite. And nucleophilicity generally parallels that. nucleophilicity generally parallels base strength, except in product solvents. This is the opposite in product solvents. For a more detailed discussion on periodic trends of acids, bases, nucleophiles, and leaving groups, you can see my other clips. Coming back to our main discussion of nucleophiles versus bases, generally nucleophiles we said are essentially the same as a base, and nucleophilicity and basicity go hand in hand. As one increases, the other increases. One decreases, the other decreases. Basically, a strong base is generally a good nucleophile, and a weak base is generally a poor nucleophile. But there's an exception to that rule. And the exception is steric hindrance. So the typical example used to illustrate this is a tertiary carbon which is bonded to an oxygen, and this is third butoxide. I'll expand this further to show all the when we observe the behavior of third butoxide, which can be written when we observe the behavior of third butoxide, we notice that this becomes a poor nucleophile. So alkyl halides that are treated with third butoxide essentially generally go through elimination in much greater and yield the elimination product in much greater yields than substitution products, which shows that this is a poor nucleophile. Using the third butoxide does not favor substitution, it favors elimination. The reason for that is, if you remember, and here I'm going to review the differences. Before even we do that, we're going to review the differences between despite their similarities, the differences between a base and a nucleophile when it comes to elimination and substitution reactions. If you remember, a base abstracts a proton, it attacks a proton. A nucleophile attacks a carbon. The base removes the proton, and the proton leaves the molecule, not taking any electrons with it, and becomes part of the base molecule. The nucleophile, on the other hand, becomes attached to the substrate and replaces the leaving group. This is the main difference between a base and a nucleophilicity. As a result, we see that a base could be as bulky. Bulkiness does not prevent the strength of a base, because protons are relatively small, and even a big bulky base like third butoxide can abstract a proton easily, because once this abstracts a proton, once one of these lone pair attacks the proton is going to become attached to the oxygen, and a proton is relatively small compared to this bulky group, this bulky molecule, and it just does not take up a lot of space, and it can easily become incorporated in this molecule. Now, if this molecule was to act as a nucleophile, this whole molecule would need to attack the carbon, to whichever the electronegative element to the leaving group is attached. This group would need to attack the carbon and remain attached to the carbon skeleton, to the substrate. And as a result, we see, and because of all these methyl groups attached to the terbiutoxide, the bulkiness of it or the crowdedness of it, and it's a good idea to actually build this molecule if you have a molecular kit, to build this out to see how the terbiutoxide looks. The presence of all these methyl groups, all these hydrogens, prevent these lone pairs. The lone pairs are hindered, and they're not able to attack a nucleophile as nicely as they would be able to if these bulky groups were not attached to this molecule. So this is an example, an explanation that the way I remember, and I encourage you to remember, for the reason that bulky bases favor elimination is because bulkiness does not prevent basicity, does not decrease basicity, does not affect basicity, but steric hindrance, bulkiness, does make a nucleophile weak and does affect nucleophilicity. And we can contrast this with an ethanol molecule. Or an ethoxide molecule to make it more similar to terbiutoxide. And we see that even though ethoxide is a much weaker base than terbiutoxide, it's a better nucleophile. So in this case, this is an example where basicity and nucleophilicity are not parallel. The weak base is the weaker of the two in the pair. The weaker base is actually the better nucleophile, and the stronger base is actually the poorer nucleophile. And the reason for that is, again, bulkiness. And at this point, I want to give you a list of bases that favor elimination over substitution. Or the basis to choose when we want elimination to be the main reaction, or we want the elimination product to be the main product. So I'm going to change title to strong, bulky, non-nucleophilic, and they're non-nucleophilic again because they're bulky, non-nucleophilic bases. So these are good strong bases, but they're poor nucleophiles and they favor elimination. And there's a few that I think you should know. When you see them, you should. This knowledge is useful in both the types of questions on your exam or your homework when your professor on your exam gives you a question. For example, I'm just going to make a random alkyl halide, and you treat the alkyl halide with a base or a nucleophile. Something that could be, and you have to predict the product. Well, based on what kind of a base or a nucleophile you're dealing with, you would make the principal product to be the elimination product or the nucleophilic product, the substitution product. Or sometimes going backwards, when on exams we're given a molecule, and we need to give a step-by-step synthesis procedure, or all the steps required to make that molecule, and you want elimination to be the principal reaction, and you want that product to be the principal product, you want to avoid substitution. Knowledge of this also helps us on which bases to use. We want to use bases, and from the list that I'm about to give you, bases that favor elimination over substitution because they're bulky and they prevent nucleophilic attack. Well, the first and most obvious one that you should know is tert butoxide. When you see that, you should know that it's a strong, bulky, non-nucleophilic base. It's a poor nucleophile. And the structure for which is, I'll write it in different forms just so you're used to seeing it in. That's the formula of it. And this could be given as the alcohol version also. That's the tert butanol. And the structure is and it's also given as the skeletal version it usually looks like a fork. Now this could be given to you with a positive metal, a cation, but as soon as you see a tert butoxide, you should think this is going to favor elimination. And one other way to draw a tert butoxide actually is just a cross instead of a fork. So when you see tert butoxide in any of these forms as your reagent or as the base being used, we know that this is going to favor elimination. I'll give you the next one, and then we'll do a summary of all the ones that we talked about. The next one that I think you should know, that should be on your list of strong, bulky, non-nucleophilic bases, would be diisopropyl amine. And just as the name suggests, it consists of two isopropyls. I'll do the structural form first, and then we'll do the line version of it. That's the structure for diisopropylamine. As the name suggests, it's two isopropyls attached to a nitrogen. And the line version of this would be The next one that we should know on this list would be triethylamine. And as the name suggests, it has 3 ethyls attached to a nitrogen atom. The fourth one on this list would be 2,6-dimethylpyridine. And the structure for that, as the name suggests, it's a pyridine molecule, pyridine ring, to which 2 methyls are attached on positions 2 and 6, on carbons 2 and 6. And then 2 bases that I often see also, depending on your choice of your professor, you might or might not be expected to know DBU and DBN. DBN is a very similar structure. DBU.